Okay, just to very quickly hit what we hit at the end of last time. It was enumerate. And enumerate was, the whole value of the for loop was, it made it an easy way to loop over each thing in a collection of things. But sometimes we really did also, we want to loop over each thing in a collection of things, but we want to have each number along the way. And the one way to do that is to do for I in the range of the length of the haystack, and then we take haystack and index it, but then we're losing some of that magic of why we like the for loops. The nice syntax is a big part of it. So that's where enumerate came in. Enumerate allows us to loop over everything while also keeping track of the index. And this would be like the syntax, example syntax, for I, an element, in enumerate another list. To be clear, I always forget which one's which. Whenever I use enumerate, I never remember, is it the element that comes first or the number that comes first? I can't remember. But I just try it, figure out what happens, and then work with it accordingly. This is just syntactic sugar. It's just nice syntax. That's all it is. This isn't something this isn't a core programming principle. No, no, no. In fact, this is just syntactic sugar, and this is a Python thing. All right? Any last questions about lists and those loops that we were hitting? All right. Now, I'm going to piss everybody off. All right? And the reason you're going to get angry is it's not my fault. It's actually going to be your fault, because I've been very careful with my wording, for the most part, to make sure I wasn't ever misleading you. But based on your intuition has probably misled you a little bit about what's happening in the computer. So this whole topic is going to it's going to really emphasize what's happening, and it's going to give you an intuition that why, when you write code a certain way, it acts a certain way, and not another way that you might expect it to. But I'm going to explain what's happening in the computer, more or less, in an attempt to make it make sense, and so you won't make the mistake that every new programmer makes a million times. Maybe you'll only make the mistake 500,000 times. So I'm going to warn you, this is going to annoy people, but trust me, it's really not too bad. But you'll have to be, this is a very critical, important topic. You're going to want to make sure you're really paying attention to this one. Because this one is kind of like an inflection point in the course, where a lot of what we're going to do going forward really all comes down to this topic. So for those of you that aren't here today, good luck. And everyone who is here, when I start getting questions about this, I want you all to laugh at the people who aren't here today, okay? All right? Before I continue, a warning. I'm going to present these ideas in a way to give you the intuition as to what's happening. I'm going to simplify some things. So if there's some jerk in the audience that's going to say, well, technically it actually works like this, you're not impressing me, I know. I'm explaining it to you in a way to make it make sense. I'm not dumbing anything down. No, 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 no. I'm just skipping some of the real funny technical nuance, especially that nuance that comes down to different programming languages. Python's actually the weird one when it comes to a lot of these popular programming languages. So a lot of what I'm going to say has a lot of asterisks attached to it in Python, but it's not actually going to mislead or trick you in any way, because really what Python does is Python really acts a different way, but it pretends to act this way to be aligning with all the other big popular programming languages. So just a warning that there are some differences. There's going to be several asterisks I'm going to skip because they really aren't important for us. And another thing I'm going to emphasize too, we like to count in base 10, right? Why? I'm not 100% sure. Maybe it's because we have 10 fingers. But we like base 10. Base 10 meaning we have 10 symbols for counting, right? If you include 0, we've got 0 through 9. And then what comes after 9? 1, 0. And you know what's interesting about 1, 0? Is really, does this marker work? Here. No making fun of my paint skills, especially because this isn't the great position for it, but when I have the number 9, right, really I've got the number like 0, 9. In fact, I've got like an infinite number of zeros that come before the 9, but we don't draw them because they're not meaningful, right? But if I have the number like 0, 7, what comes after 7? Go back to grade 1. 0, 8, very good. You didn't need to say the 0, but that's okay. 0, 8. What did you do? Well, you went to the symbol that comes after 7. What comes after 8? 9, yeah, because it's the symbol that comes after 8. What comes after 9? Yeah, I mean, it's funny. We're out of symbols, but the trick is you bring this 9, you just return it back to the 0, but you increment the next digit, right? So we've got 10. So, by the way, when we're talking binary, if I've got the number 0, if I've got the number 0, what comes after? Remember, with binary, we only have 2 symbols. So what comes after 0? 1. Remember, with 0, really, it's like 0, 0, 0, 1. Now, what comes after 1? 2, but we don't have a symbol for the number 2, because in binary, we only have 2 symbols. We have a 0 and a 1. So we actually do exactly the same thing we did with decimal numbers. You reset this digit, this bit, back to the beginning, which was 0, and we increment the next one, and that's 2. What's really interesting is 1, 0, depending on the base you're in, 1, 0 always means the base. So 1, 0 means 10, base 10. 1, 0 means 2 in base 2. Which is kind of neat. So what comes after 2? 11. Yeah, good. Right, because you increment this. Great. Now what comes after? Now remember, really there's a leading 0 before all of these things here. So what comes after 11, which is 3, of course? 100, which is 4, because, well, you flip this over to 0, you go to the next one and you increment that. Oh, we're out of symbols. So that goes back to 0. And then you increment the next one. There. But that's exactly how it works in decimal. It's just we're doing it with less digits. Now with hexadecimal, hexadecimal is base 16. Meaning we actually have 16 symbols for different numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But what comes after 9? Does anyone know? In hex? What were you going to say? Nailed it. A. A means 10 in hexadecimal. B means 11. C, 12. D, 13. E, 14. F, 15. But there's no 16, because remember, like with 10, with base 10, there is no symbol. There's no one symbol that means 10. We have 1, 0. So in base 16, we have 16 symbols, but one of them 0. F means 15. So if I have 15, so if I had like, okay, E, that means 14. I increment that. I go to the next symbol. F, that means 15. But what comes after F? Well, there is nothing. So we go back to 0, and you increment there. So 1, 0 in base 16 actually means 16. All of this is to say, this is not on the test. Traditionally, when we're talking about memory addresses inside of a computer, we use base 16, not decimal numbers. But for simplicity here, now that's arbitrary. We could use any numbering system we want to count. For simplicity here, I'm going to use decimal numbers. This is just to hedge against that asshole in the room that goes, technically it should be base 16. I know. So just be warned. I'm going to treat them like as if they're decimal numbers. So here's an idealized view of RAM. Raise your hand if you know what RAM stands for. 1, 2, 3 people. It means random access memory, right? Raise your hand if you're like, actually I knew that. I totally knew that. Only like 2 more people. All right. RAM is basically when your computer's running, all of the stuff that's currently happening is in RAM. Your hard drive, or maybe you've got like a solid state drive, fine. But that's like longer term storage, that type of storage. That's like your pantry and your fridge. RAM is your countertop. That's where you're doing everything, right? You just kind of want it there. It's easy to access. You can get to it quicker and use it easily. Obviously, if you have a bigger countertop, that's better, right? You've just got more room to work with, which is really nice. If I want to make a cake, I don't want to do it on a desk like this. It's going to be harder. I can do it. I just have to keep going, putting things away, getting them again. A lot of back and forth. That's slow. So here's RAM. And here's an idealized view of RAM. We pretend it goes on forever, but it doesn't. And each RAM is broken down into memory addresses. There's an address for, it's like a lookup table. Go to memory address, whatever, like an address on a street. You can think of the street, the house address as the address of RAM, and the house itself is what's in that memory address. And we put our contents in RAM. How much space we put for each memory address is, it could be arbitrary, whatever. But for our purposes, like integers and other primitive types, raise your hand if I've mentioned primitive types before. So primitive type, that's something like an integer, an individual character, which really doesn't exist in Python, an individual character, floats. Those are your primitive types. What we like about them is I know how much room I need. I know how much RAM I need to store an integer. All integers are going to fit into 4 bytes. And for those of you that don't remember, and this isn't overly important right now, 1 bit is a 0 or a 1. 8 bits we call a byte. And traditionally, we're storing an integer or a character or a float in 4 bytes, which is 8, 16, 20, 32 bits in total. So we would put 32 bits for our purposes here. We're going to pretend each memory address, which we can think of this right here, is actually 4 bytes, but the point is I can put an integer in there. Does anyone know what we call half a byte? No one in the other section knew either. And I'm not joking. This isn't a joke. It's called a nibble. 4 bits is called a nibble. That's not a joke. It's hilarious if you ask me, but it's what it's called. So this is just saying what I already said. If I come along and I were to write something like x equals 17 in Python. So I go here, and I say, okay, x equals 17. Right? Here's what your computer has to do. Your computer goes, okay, the integer 17. Great. I can shove that into a memory address, no problem. So I'm going to go find a memory address. In this particular example, for our purpose, consider this as entirely arbitrary. It doesn't really matter where it goes. All that matters is that we remember where we put it. So your computer's going to go, okay, 17, I'm going to put that memory address 126. And I'm going to assign a label to that memory address, and that label is X. So there. X is 17. 17 is your computer takes 17, puts it in some memory address, and then labels memory address 126 with the label X here. All right? So this is what's been happening. So far, so good? Any questions? Now is the time to ask. This isn't the weird part yet. Now, listen very carefully. If I wanted to make a copy of the value X that X has, I would say something like Y equals X, right? Right? This shouldn't spook anybody. This should be this should be well understood at this stage. So what's the computer doing? Now everyone pay very special attention to exactly what I'm saying. Because this is the root of where issues start to come from. But by being clear and listening carefully to what I'm saying, I'm hoping to eliminate these issues. When I said Y equals X, the computer goes, and now listen, and it goes to the memory address associated with X, 126. It takes the contents of that memory address. What's the contents of memory address 126? This isn't a trick question. 17. It takes the contents and makes a copy of the contents. What's the contents? Contents 17. It's an integer, right? And I put it somewhere else. The computer decided it's going to put it in memory address 129. Entirely arbitrary. It could have been a memory address 2 million. It doesn't matter. But it made a copy of what was in that memory address. And then it made a new label Y and associated with that. So what was actually copied? 17. The thing that was copied was the value in that memory address. Say it with me. The value. I'm not joking. Say it, because you're all going to mess this up, and I'm going to say, I made you say it. The value in the memory address. You're experts. Perfect. You didn't have to repeat that, but you could. Right. Now, we have a list. And as we were talking before, just like with strings, lists and strings and other objects are basically not your primitive types, things that take up an amount of memory that I don't really know. If I have a list, if I have the single number 17, and the computer has divvied up the RAM into 4 bytes, I can shove an integer into one of those seats, because the integer fits nicely into 4 bytes. It's happy. The problem is, how much room do I need for a list? Well, that depends. Does the list have 1 number in it, 2 numbers, 2,000 numbers? I don't know. But if, for example, I have this list, now I'm using the labels A through H. These are just arbitrary labels. They don't matter. They don't mean anything. You could think of them as integers. But I have a list of 8 things here. A, B, C, D, E, F, G, H. Each of those integers needs 4 bytes. Meaning I need a total of 256 bits, or 8, 16, 20, or 32 bytes to store all that information. So how the hell am I going to store a list of information in memory? I obviously can't do it like I did it with a regular integer. It's not going to work. I can't shove 8 integers into 1 seat. It's not going to happen. This should be pretty obvious, right? If I told 8 of you to sit in that seat right there, you're going to go, I can't. And you got to remember, when we're talking about memory addresses and whatnot, there are literal physical locations on this computer that we're talking about. They're itty-bitty, but they're physical locations. So it's not like, oh, you know, it's virtual, whatever, we just shove them all. No, there's physically no more room. So what do we do? Well, here's what we do. Is the computer, here's the solution. The computer will find a chunk of RAM, for simplicity's sake, a contiguous chunk of RAM, where it can store those values. For example, it just so happened, and again, I can't stress this enough, the memory addresses that it picks, entirely arbitrary. I don't have control over it in Python. The operating system's dealing with this stuff. The memory address that it decided, the memory addresses that it decided to put the list was, well, start with, okay, let me take a step back. I have 8 integers. Well, why don't I just put 1 integer in a seat and do that for each integer and then just remember where I put them? Like imagine right there, I got 4 of you. There's 4 of you right there. You're I got a list of 4 integers, and that's what the computer said. Okay, first there's you, and then you, and then you, and then you. There. You fit. But, I mean, now, how is the computer going to know, though, right? There's a lot of information here that needs to be remembered. There's a lot of bookkeeping that needs to be involved. Sure, I shoved that data I wanted to store into RAM, into memory addresses 677 through 684. Again, arbitrary values, but that's where I put those 8 values. Remember before, when I stored the value 17 with the regular old integer, a primitive type, I put it there, and then I had the label associated with that memory address. So what I'm going to do now is something like this. If I wrote Z equals A, B, C, D, E, F, G, H, the computer goes, finds a chunk of RAM to store that list, but it makes a variable, Z, and what's actually stored in Z is not the list. The list is not stored in Z. When I run this and I print Z, I see that list. Z is a variable, but Z doesn't store a list. It's not. I'm not being silly. There's no ifs, ands, or buts. It's not storing a list. X stores the integer 17. Y stores the integer 17 because it got copied from X. Z, it's not storing a list. Instead, what it stores is information about that list. For our purposes here, Z stores a reference to where the list is. Because the label Z has to be for a memory address. I don't have a single memory address that I want to store because I've got a whole list. There's a lot of information there. So instead, I put the details about the information I really want to store, the list, in memory somewhere and associate Z with that. So when I have this here, Z equals some list, Z is not the list. It's not. It's a reference to a list. X stored the number 17. Z does not store that list. It stores a reference to the list. Big difference. So whenever I want Z, the computer has to go, okay, Z. Oh, okay, well that's actually a reference, and that reference is to here. That's how it's going to work. All right? Any questions so far? Again, now's the time to ask. And if you have a question that you think you might want to ask, chances are half the people in the room have the same question. So be their hero. Yeah? Well, actually, interesting that you just asked that, because that's the next thing. When you're looking at this image here, I'm going to quiz you. I'm putting you on the spot because you were brave enough to ask, so you're brave enough to answer. Z stores the start of that list. Z says, oh, there's a list starting at memory address 677. And I know I've talked about this before. But when you're looking at this, think to yourself, why do we start indexing at 0? Yeah. It means go to 677 and stay there. If I said Z at index 1, that means go to the start of that list and take one step. And where are we? Well, we're at B. Indexing is actually just syntactic sugar for like memory address arithmetic, for doing arithmetic on these memory addresses. Really, it is, traditionally speaking. But, just one sec. Back when the next semester course was in the language C++, C++ will actually allow you to do things like memory arithmetic, pointer arithmetic. New languages don't let you do that because you shouldn't have to do that and you don't want to do that. In fact, even the American NSA has come out and saying, like, stop using these programming languages. They're dangerous. They're like literally national security issues. But we were using C++, and even then, I'd made the students do the arithmetic to show that indexing was doing the same thing as the arithmetic. And even then, like, the computer would be like, when you'd hit run, the computer would be like, are you sure you really want to do this? I don't think you want to do this. And you could be like, yeah, shut up, go. And it would. But it would even warn you. But that's not that important right now. Yes?
So it stores the location for where it started listening, but how does it know how long?
So I'm talking very traditionally here. Now, other pieces of information are actually stored here, not just where it starts, but a whole bunch of like facts about that list that we could remember, like how long it is and whatnot. So that's why, like, if I were to say Z at index 17, Python's going to go, there's nothing there, right? But in some of these more traditional programming languages, these older ones, if you said Z at 17, it would go, okay, 677 plus 17, what is that, 694. It would go to memory address 694 and be like, here you go, which of course isn't in the list. But it's like, you must know what you're doing. You asked for this. And that's another example of why these languages are pretty not safe. So, anyways, more than just 677 is stored to answer your question. Other questions? Yeah?
Sorry, kind of, I guess, in follow-up with that one, is it kind of storing it as if it was like 677 and kind of like a colon until 684?
No, there's a lot of nuance. You could think of it like that if it helps, but how it's really happening, it's entirely different, right? But there's a lot more going on there. There's a lot of facts about it, right? Like, well, what's type in there? What's its length? When's its end, and et cetera. There's a lot. We're going to actually learn a lot more about like this type of stuff once we get to. So the problem is this. In Python, this actually works quite differently in reality, but this is traditionally how things work, and it explains why what I'm right about to show you does what it does. But we're going to learn more about objects in a couple of topics from now, and all of this is going to become a lot clearer to you. Yeah. All right, any last questions? So, let's go back for a moment. I wanted to make a copy of x. I said y equals x. And you said with me, when I did that, the computer went to x and made a copy of the contents of x and put it into y. It copied the contents of x. If I want to make a copy of W, of Z, I say W equals Z, just like this. I'm going to print out W. And we see, oh, there's the list. But if you've been paying attention, what is the computer going to do? The computer goes to Z, makes a copy of the contents of Z, puts it somewhere and gives it the label W. What was in Z? Was it a list? No. It was a reference to a list. When you look at this image, when I made a copy of the integer 17, after that, how many 17s are there in RAM? 2. When I made a copy of Z, how many lists are there now in RAM? 1. I didn't copy a list, did I? I copied the contents of Z. What was in Z? A reference to a list. Meaning, I only have one list, but I have 2 copies of the references. I have 2 references to that one list. We call this situation, these are aliases. So why is this important? Well, if I go here and I say, okay, x equals 17, y equals x, and then I say x equals 99, when I hit run, don't think too hard. If you get this wrong, you're thinking too hard and you're actually not trusting what you already know. When I hit run, what do you expect to see? Were you right? You should be. Because x was 17, y made a copy of the contents, the computer made the copy of the contents of x, which was 17, and put a copy of the value 17 into y. And then I went back to x and I said, okay, x, you're 99 now. But y was left alone. I didn't touch. X was 17, y made a copy. I go back to x and change this to a 99. Y is still 17. X and y are independent. But if I go and say w at index 4 equals uppercase P, and I print out W, I see this, right? A, B, C, D, P, F, G, H, right? But now I'm going to print out Z. I see the same thing. A, B, C, D, P, F, G, H. Why? Well, let's look at what would happen. If I said W at 4 is P, the computer goes, okay, W, okay, well, that's a reference to over here. A, B, 0, 1, 2, 3, 4. Okay, you become a P. W at index 4, changing it to P, went and modified the one and only list that exists. But it doesn't matter how many things are referencing that list. That one list got changed. Every variable that references that list, when it goes and looks at that one list that we changed is changed. There's only one list there, and I changed it through one alias. You can do it again. W at 4, no, Z at 0, equals X. Well, now it looks like that, right? Like now we've got both of them are going to be X, B, C, D, P, F, G, H. There's only one list, and we modified that one list. Now, when looking at this, Here's why me showing you this is so important. If you expected the line of code, W equals Z, to make a copy of the list, this pisses you off. Right? Because you're like, well, I didn't modify Z. You're right, you didn't modify Z. You modified the thing Z referenced. Z was left alone, that's great. If you expected it to make a copy of the list, you're unhappy. But remember, the whole point of this topic right now was it doesn't make a copy of the list. It makes a copy of the contents of the memory address. And the contents of the memory address was a reference. It copied the reference. If you remember that on October 20th, 2023, I told you it copies the reference, then this makes perfect sense. Absolutely. I am going to say, and here, let me say this one last thing here before I say that other thing. If, after all of this, give me a second while I think of a good solution. Okay, W equals Z. W at 4 equals P. And Z equals now, I don't know, 5, 6, 7, 8, 9. Look at this code. I'm going to give you 30 seconds, no, 20 seconds to look at this and come up with what you're going to expect to see when I hit run. Nothing about this is a trick. There's no trick here. If you just follow what we've been learning and what we just talked about today, you'll get the answer. So I'll give you 30 seconds, look at this, come up with an answer in your head, I'll hit run, and you'll let me know if you're right or wrong. All right, can I hit run? You ready? You got your answer locked in. Now you need to be honest. Raise your hand if you were right. Raise your hand if you were wrong. Now let's talk about it. So, if you're right, good for you. If you're wrong, you were working too hard. Classic programmer mistake. New programmers always try to connect dots that don't exist because programming is supposed to be hard, right? No, programmers are too stupid to do anything hard. Z, we make a list. I'm going to draw. I'm going to just represent these lists. I'm not going to draw them all out. I'm just going to just draw like a circle. There. So now I have Z is that circle, right? Oops, oh, I had it the right way. Then I said W equals Z. So going back to this, we know that just makes a copy of the memory address, which really is, for simplicity, W just copies the reference. I have two variables that reference the one same list. So far, so good? This is just my simplified representation of what's happening in RAM. I just didn't draw the memory addresses. Right? If Z was the list, I would have wrote it like this. Whoa. Right? But it's not. It's a reference. So Z really is the arrow, not the list, which is the circle. I said W at index 4 becomes P. All right, so I go into this list here, and I change something about it. There. I changed it. Something about that list is different. Its state is different. So at this point in time, right here, after those 3 lines of code, if I said print Z, I get this green thing with the blue in it. If I said print W, I get this green thing with the blue in it. But then I say, oh, okay, go make a new list and have Z reference it. So the computer goes, okay, great, I'll go make a new list. There's my new list. And did I say W? Oh, no, I said Z. Shoot. No. Okay. And then I said, yeah, Z, you reference it. So it goes, oh, okay. There. Put this back. That's what happened. I made a new list. If you were thinking if you thought that after W equals Z, it made Z and W inextricably linked to one another, no. All it did was copy the contents of what was at Z and put it into W. Then on the line of code, Z equals this, I changed the contents of Z, but it left the contents of W alone in the exact same way doing this worked. There's no tricks. The important thing is you understand what's in that memory address. And once you do, you're good to go. There's no trick. Copied over X into Y. Okay, great. So I copied the contents. But they're not, sure, they're similar. They're related in that they store the same value. But the variables themselves are independent. Yeah? Yeah. Now, just as a note, and to be clear, there's actually a lot more to this than what I'm about to say, but really, what's happening here is when I have a list, I'm not really storing those integers. Those integers are actually, there's actually like another layer of this, where what's stored in that list is actually memory addresses to memory addresses of where the values are actually stored. And in reality, you could play this game forever. The computer will happily do that. But thank God Python hides a lot of this from you. Now remember I made a big stink about strings are immutable, right? Right? But lists aren't. Right? But I made a point to say we really like the immutableness. We like the fact that once you make a string, you leave it the hell alone. You can't change it. And if you want to change it, you still can't. But you can make a copy of it and modify the copy. You can do that. But the string itself is left alone, right? But with lists, no, you can go in and screw around with them like I showed you. Like in this example, I'm going to get rid of this last line here. We can go in and screw around like this. Now, even though, I'm sorry to say, even though I've explained this to you, you're going to mess this up. It doesn't matter how experienced of a programmer you are, you're going to mess this one up. Raise your hand if you've started working on assignment 2. Raise your hand if you were working on the infect city and most of your assert tests passed, but the last few didn't. The tests that had is, were those the ones that failed? You can't remember? It wasn't for you? That right there, if all the tests pass except that is test, It's because that right there is related to everything we were just talking about here. When you look at this code, the fact that I have references here, and then I was able to go and modify that one single list that exists through another reference, could you imagine that this phenomenon right here, this scenario, could A, cause bugs, and B, be a giant pain in the ass to debug? If I've got a billion references to things, and one of those references happen to modify that one thing, I'm screwed, right? That's one of the reasons we like immutable things. I could have a million references to one thing, but if I can't go in and change it, whatever. What was that noise? If I can't modify it, then there's no risk of this mistake happening. If you really want to modify it, make a copy and modify the copy. You're good to go. And that's what I'm having you do in assignment 2, and that's probably why all those is tests are failing. Listen to me now. If you start working on assignment 2 and you're doing like infect city, and the first few tests pass where it checks if the before city and after city are the same, but then you ask, like, if you get to the is tests, the asserts that say like, not city A is city B, and they fail, it's related to this. There's a hint. So we really like the immutableness because it eliminates this potential issue right here. Any last questions about this? No? Yeah?
So what's actually being stored in like each address? Like you see how in the one section when it was an integer, you could have 17, which was like 2 characters.
It's not characters, it's the integer. You got to remember, we write the symbols 1, 7 to mean the number 17. The number 17 isn't intrinsically 1, 7, right? I could have 17 things in front of me and I could be like, there's 17 things here, but there's no 1, 7 floating around in the universe about that. So what's actually stored there is a series of zeros and ones that get decoded to 17. And remember my whole thing about how zeros and ones, if I ask you, what does this mean? You can't answer that until I tell you, what was it encoding? I can't tell you what that binary, those zeros and ones mean unless I know what it was encoding. And remember how I opened up that video file in the text editor and it was a bunch of gibberish? That's because I told the computer, read this as if it's text. And the computer's like, okay. But it wasn't text, it was actually video, and that's why it was all nonsense. So having that, continue to ask your question. What's actually stored is the 32 bits, 32 zeros and ones, that one getting decoded as an integer means the value 17. Yeah.
Scale with characters.
Now, for now, let's say no. Now, come back in a year, and then we can really dig into that. Good question. I saw a question over here. Yeah.
So the only way to truly copy a list is to just like put the list in again as a separate.
There's a couple of ways we can do it. Here's the easiest way. Look, it's different. I actually made the copy of the list. So when I modified W, it modified W, but Z was left alone because they're separate lists. There's an arguably easier way to make a copy. It's with slicing. Give me the list from everything from the beginning to the end. That'll work too, but I don't like that as much because .copy is a little bit more clear. Yeah. All right, remember, questions, thoughts, concerns, want to chat, come to student hours, please. I get lonely.